Section 4.3 and 4.4, Logarithmic Functions and Their Graphs. In these sections, we'll convert from log to exponential form, convert from exponential to log form, evaluate logarithms, use common logs, and use natural logs. So, we've been working with the exponential growth formula f of x is equal to ab to the x, and here's a problem that we had posed earlier in a section. The population of China was about 1.39 billion in 2013 and growing at a rate of about 0.6% per year. Predict the population of China in the year 2020. So we did this problem by taking our formula, using 1.39 as our initial value, and coming up with a growth rate of 100% plus an additional 0.6% per year. That would be 100.6% per year, which we would then write as a decimal. So our growth rate would be 1.006, and we could go ahead and make a formula for the population growth of China. It would look like this. F of x is equal to 1.39 times 1.006 to the x. And x would be our time. So if we wanted to predict the population of China in the year 2020, if time started in 2013, that would be an x value of 7. All we would have to do is replace x with 7 and put this into our calculator. But then we posed a different question. If the growth rate continues, when will the population reach 2 billion? We were able to set up that problem. 2 is equal to 1.39 times 1.006 raised to the x power. But the problem we had was that we hadn't discussed in our class how to solve problems or how to solve equations where the unknown, the variable, is in the exponent. So finally, we're getting to a section where we're going to discuss a new function that will allow us to solve this type of equation. So this type of equation is called an exponential equation because it's an equation where the variable is found in the exponent. And to solve an exponential equation, we'll need a new type of function called a logarithm. So the log function is the inverse of the exponential function. It's the function that undoes the exponential function. That's why it's going to allow us to solve exponential equations. So the first thing we have to do is translate from exponential equation into log equation. So if we have an expression like a is equal to b to the x, and this is in exponential notation, to translate it into a log equation, we would write log. The base we would write here as a subscript, and it's always equal to the exponent. So these two expressions are equivalent. So the first thing we're going to do is we're going to practice translating from exponential equation notation into log notation. So for example, 2 to the third power is equal to 8. Let's write that using a logarithm. Log, the base is 2. It's always equal to the exponent, so we have log to the base 2 of 8 is equal to 3. Let's try the next one. 3 to the negative 2 power is equal to 1/9. We write the word log. The base in this problem is 3. It's always equal to the exponent, and so we have log to the base 3 of 1/9 is equal to negative 2. One more example. 4 to the 1/2 power is equal to 2. So to translate that into logs, we write logs. The base is 4. It's always equal to the exponent. So log to the base 4 of 2 is equal to 1/2. Here's one for you to try. Write 27 to the 1/3 power is equal to 3 using log notation. Now we've just practiced going from exponential notation to log notation going in this direction. So now what we're going to do is we're going to practice going backwards. Given log notation, write exponential notation instead. This direction is a little easier because we're more used to seeing exponential notation. So log to the base 2 of 16 is equal to 4. We'll rewrite that using exponential notation. The base is 2, the power is 4. 2 to the 4th is equal to 16. Log to the base 9 of 3 is equal to 1/2. The base is 9, the exponent is 1/2. 9 to the 1/2 power is equal to 3. Log to the base 4 of 1/64 is equal to -3. The base is 4, the exponent is -3. 4 to the -3rd power is equal to 1/64. Now you might wonder, well, why do we practice going back and forth between log and exponent notation? Because that's how we're eventually, in a little while, going to be able to use logs to solve an exponential equation. So one use of logs that we in California are pretty familiar with, although we may not have thought about it this way, is with our Richter scale. So the Richter scale is a base 10 log scale that measures the magnitude or the power of an earthquake. So the ratings are based on the amount of energy released during the earthquake. In 1989, the Loma Prieta earthquake had a magnitude of about 7 on the Richter scale. And the most powerful earthquake ever recorded in North America, and the second most powerful in the history of the world actually, was the 1964 Alaska earthquake, measuring a little over 9 on the Richter scale. So what does a difference of 2 on the Richter scale mean? The number 2 seems like a very small number, but what does it mean in terms of the difference between these two earthquakes? Well, again, the Richter scale is a base 10 log scale. So when we say that the Loma Prieta quake was about a 7, we are talking about a magnitude or a release of power measured in about 10 to the 7th, where the Alaska earthquake was a little over 10 to the 9, a little over 9 on the Richter scale. That had a magnitude of 10 to the 9th. And if we were to compare these numbers, that means that the difference between these two numbers is 10 to the 2nd, or in other words, 100. So the Alaska quake was actually 100 times more powerful than the Loma Prieta quake. So that's just a little bit of California use of logarithms. Let's take a look at the graphs of the log function.